connection to PP collisions where both for K star and phi, they are pretty flat. So we fit it to get this value of rho 0, 0. If it's 1/3, there is no spin orbital angular momentum interaction or spin alignment is not there. Let's look at the rho 0, 0. So what is plotted here in the y-axis is rho 0, 0. X-axis is the transverse momentum of the vector meson. And these are the data points for lead-lead collisions at 2.760 eV, mid-central collision where we expect the effect to be maximum. This line is no spin alignment. At higher PT, they seem to be consistent with 1/3, and then there are some deviations of rho 0, 0 at the level of 2 to 3 sigma from 1/3. The boxes are systematic uncertainties. These lines are statistical uncertainties. We do the same thing with production plane. Again, high PT, they are consistent with 1/3. At lower PT, slightly, central points are slightly above the event plane, but there are some deviations from 1/3. This is production plane. Now we look at the proton-proton collision where there is no initial large angular momentum. They are consistent within the uncertainties with 1/3. And we can put the K0 short results, and again they are also pretty consistent within the uncertainties with 1/3. So that is what we observed. Here is in the totality with respect to event plane, K star, phi at a level of about 2 to 3 sigma, K shorts. With respect to production plane, PP collisions, and random plane, this small deviation of this data point we understand, and I will refer to it later on for the random plane. Now let's look at the collision centrality dependence. This is rho 0, 0 as a function of number of participating nucleons. Large number of participating nucleons means small impact parameter, head-on collisions. And small number of participating nucleons means peripheral collisions or grazing collisions. The blue data points are for high PT. The red data points are for low PT. There are two planes, production plane, event plane, K star and phi. As you can see, for high PT, there is no such, rho 0, 0 is consistent with 1/3. At lower PT, there is a centrality dependence. For large impact parameter and small impact parameter, it is tending towards 1/3. More deviation in mid-central collisions for K star and also for phi. So these are the results. Now we also try to figure out, is there a relation between the production plane and the event plane results? They are related through the collective phenomena V2, and we did a simple model calculation to understand this hierarchy of rho 0, 0 with respect to event plane, production plane and random plane. This randomization has been done here in 2 dimensions, so there is still a common axis, and if one does a 3-dimension randomization, which we did subsequently, and it is consistent with 1/3. So that's the connection between the 2 event planes. So let's see whether it qualitatively agrees with the theory expectation. The theory expectation was that since the angular momentums are maximum for the mid-central collisions, you should expect the phenomena, what you observe, to have maximum effect there, and going to small values at both the ends of the impact parameter, and that's the trend it seems to show. The other theory expectation was the transverse momentum dependence. If the picture is that there is polarization of quark in presence of large initial angular momentum, and subsequent hadronization is through recombination process, and that's what we observe, that at high PT they tend to be 1/3, and then there are deviations of the level of 2 to 3 sigma at low momentum. Recently, RIC has its revised results. These are phi mesons. They see and the momentum ranges are above 1 GeV. The phi meson results are positive at low root s, and if you integrate the Alice results, that's what they have done. Within this high, this momentum range, then this is where the phi sits. And K star sort of fluctuates, and this is where the Alice result sits. These results are now revised at rig. The phi meson result on totality is mentioned in this work to be at a 8 sigma level, and this line is a model expectation which invokes a new kind of coherent mesonic fields in order to explain the observations at rig. So the summary so far is there is an evidence at the level of 2 to 3 sigma, but at rig for phi mesons at the level of 8 sigma of spin alignment of vector mesons. These measurements seems to be coupled to the event plane and vanishes when we randomize it. That suggests that they are related to the initial angular momentum effects. It is not observed for proton-proton collisions where we do not have a large initial angular momentum. It's also not observed for spin zero particles. Now, I must also let you know that some time back, Rick has, as well as Alice, has measured polarization of lambdas. Lambdas are baryons, spin half carrying particles. The angular distributions can be worked out to look like this, and where this represents the polarization. These are measured here, percentage as a function of collision energy, and there is finite polarization measured for lambdas at lower collision energy. Invoking a particular model, if we convert the entire polarization measured to vorticity, that's a caveat or an assumption. Using this expression and putting typical values of temperature, the vorticity would be of the order of 10 to the power 21 per second, rotations per second. Just to give you a perspective, we encounter these vertical effects in many systems, including the coffee when we are drinking, or when you take a flight, or in the rivers, or the tornadoes, or this is not a sunny, but I think this was funny cyclone. And these are all rotations of the order of 1,000 per second, but if you convert the entire polarization measured using the hyperons, then it is quite large. So it's a that's why people tend to say it's most vertical fluid as observed in a laboratory. Now these measurements which I showed you are very challenging and statistics hungry, mostly dominantly at low PT, where the reconstructing these vector mesons are difficult. But it also, if they stand, at the moment there are about 3 sigma effect. If they stand, then they bring in a lot of surprises also. Suppose you try to convert whatever rho 0, we measured to polarization of the quarks. They give large values, larger than what is measured for hyperons. If you try to also extract again in a model way the polarization of the vector mesons, they turn out to be quite large. Whereas the general trend expectation is that the polarization should reduce as you go to higher collision energies. So there are some work remains to be done to figure out or reconcile these effects that one sees. There is work both on theory and experiment side. On the theory side, these measurements possesses some challenges. From the experimental measurements possesses some challenges. How to reconcile the polarization measured, small polarization values measured with the hyperons with the spin alignment of vector mesons. The values are less than 1/3 for K star, greater than 1/3 at least at rig for phi. So that would need a development of a proper relativistic spin hydrodynamics, and that is an area which is an ongoing in our field, like the collective elliptic flow measurements triggered the development of relativistic hydrodynamics. Now spin has to be included, or is being included. Then models with conservation of angular momentum and has to be there, and what fraction of this initial angular momentum gets transferred to the QCD matter is something which has to be figured out. And when we are dealing with hydrodynamics, we are dealing with fluid, whereas spin is a sort of a, finally they hydronize to particles which have spin. So how this transfer of spin happens from a fluid to particles is again another topic which needs a lot of clarity. From the experiment side, higher statistics data is available, 5 dB. Here are some preliminary results that they tend to follow the same 2.76 results, but there is much more data. One has to look if the signals improves or what happens there. Same is with RIC. The phase 2 of beam energy scan program has taken a huge amount of data. So we will see how those results unfold. It's important to look at lambda and anti-lambda polarization separately. So too for charged K-star and neutral K-star. For example, their magnetic moments differ by some factors which makes them sensitive to, maybe sensitive to initial magnetic field. So these are exciting times. So establishing and a proper treatment of initial conditions in heavy ion collisions could have impact on physics and discoveries in this area. And please stay tuned to such interesting results from heavy ion collisions. So with this, I would end my talk with acknowledgements to Alice and STAR collaborations for those exciting results. And theory colleagues, thanks to the organizers for the invitation. I would also take this moment to say that the Indian group is in these two experiments due to guidance and very starting of this heavy ion program by Professor Sinha, without which we, including myself, wouldn't have got this opportunity to be part of this experiment. And personally, it's a tremendous support from him. I think very positive and tremendous support always there for our work and specifically for my work. So thank you, sir, very much for your support. And thank you very much for listening.
Thanks, Vedant, for a beautiful talk and on time. Now it's open for questions. Yeah, Sushanta.
Vedanta, your very interesting and clear presentation has raised some questions in my mind. And if I may ask you, the first one is a very trivial one. You use the fact that trace of rho is equal to 1, so to relate everything to rho 0, 0, which implies that rho 1, 1 and rho minus 1, minus 1 are very simply related. Are they equal?
Some combination of them are equal. But we could actually measure more differential and get access to those elements.
Okay.
That can be done.
All right. My second question is, as you know very well, you mentioned the spin-orbit interaction, and as we know in atomic nucleus, it comes from the electric field of the nucleus, the protons and other things at the site of the electron. And special theory of relativity says that when you go to the rest frame of the electron, that electric field transforms into a magnetic field and gives you the spin-orbit interaction, which you said is responsible for fine structure splitting, etc. Now, this will happen even without the presence of a magnetic field. And as you said very clearly, that in spintronics, it has raised very interesting phenomena due to Rashba and Dresselhaus. Now, question, Vedanta, is that if there is this very large magnetic field also, then that magnetic field, in addition to the spin-orbit interaction, would have Zeeman interaction with the spin, which is what you probably indicated for the lambda particles in the theory paper, as well as Landau diamagnetic interaction to charge for the orbital motion. So you have Landau physics, you have Zeeman interaction, and on top of that spin-orbit interaction. So how do these things combine together? And my last question very quickly. When you talk about the phase transition, you go from a chiral symmetric phase to a chiral broken phase. And so as you go across the transition, the breakdown of chiral symmetry, would that have any impact on all the results that you presented?
Yeah, no, these are important and very interesting questions. As I was showing in this slide, magnetic field has its effect in addition to angular momentum. So how they come together and what they give, that has to be worked out. These are limited statistics data which is coming out. As we go build more statistics in this high luminosity runs at LHC, we'll have more precision measurements. And then I guess theory would like to differentiate the phenomena which you suggested. Yeah, as you know, we have a lot to learn from condensed matter systems, including phase transition, crossover, what is first order. Here also, there is a lot to learn from the spin orbit interactions which we see in the condensed matter systems. But at the stage, these are just first set of measurements. More differential measurements, high statistics will answer your questions likely.
Yeah.
So, Bedanga, thank you for that beautiful talk. I was curious, when you were on slide 22 showing the RIC results, you said that there had been a revision to the analysis. Can you talk a little bit more about that, please?
Yeah, the revision is the 5 results remain same, but the K star changed. The K star results, this is again a BT integrated result which is in the paper, and little bit, 1 to 5 GeV. The results were what was shown in the quark matter, the previous quark matter were consistent with Alice. But now there is a change in the results.
What change?
They said there was some issue with the Monte Carlo data, and that's why it changed. So we will, as I was just discussing before the talk, we will figure out more what happened. It didn't affect though the phi, but it only affected the K star. So that is.
Yes, next question.
So my question is about the lambda from star. I was wondering, since there is a certain amount of polarization that can come from weak decays of higher strangeness hyperons, I was wondering how well this is under control in the star
Yes.
analysis.
So now star is starting to measure heavier hyperons and trying to get a handle on that part. But what you said is correct. There is a uncertainty coming from these decays, weak interactions. Yeah.
Because
The lab, first of all, this is a very elegant talk,
Thank you, sir.
very clear, it's a complicated subject. Now, I have known about this work for quite some time, and my friends, I was very excited when I went to CERN last time. There was a billboard sort of advertisement about this talk in the CERN lecture theatre, which is very nice and gratifying. My question is that, two questions. Do you have any clear idea after this work about the order of the phase transition? Order.
Yeah.
Then if it is a crossover, so you have the same effect as opposed to first order.
Yeah, how that is going to affect this, I do not know. But what the theory calculations suggest is the energies where we are, it's a crossover. That is what the theory suggests, that at small baryonic chemical potential, whether it is top LHC energies or Rick energy, it's a crossover. First order is looks like way down the phase diagram, mu b, at least not anything below 200 MeV mu b, or it has to be greater than that. So this is mostly in a crossover regime we are looking at.
Okay, if it is crossover, then there should be some signals of the hadronic system being carried through somehow to the QGP and hadron mix, you know.
Yes.
Yeah.
Yes. And hadronization does play a role in the value what we finally measure, because what we are measuring is using hadrons. Whether it is recombination or quartz fragment into hadrons also plays a role for this alignment.
Sorry, Mr. Chairman, another little question. You see, the plasma is flowing with time, okay? And presumably there will be a lot of collisions as you go along to the final non-interactive state.
Yes.
I just wonder how much of the spin-orbit business or existence of spin-orbit gets washed out by collision.
That is again a very nice question. That's why we were looking at the two different vector mesons. One is a short-lived 4 Fermi K star, and the other is 10 times larger lifetime phi, which is 40 Fermi, trying to see if there are differences, because the K star will decay to K plus K minus, and then this K plus K minus will scatter. But then we found out that this K plus K minus, if they scatter, their momentum changes, so we will never reconstruct the K star also. So what we are measuring is reconstructed K star. That means their daughter particles are not scattered that much. But we do see a difference with respect to phi, which differ by a factor 10 in their lifetime. What is the reason, we do not know, but there are some differences.
Vivek, you have a question there.
Actually, if I could quickly ask, the magnetic field estimates you showed, were they based on equipartition?
The magnetic field,
The theoretical estimates, were they based on assuming equipartition?
As far as I remember, it is just using electrodynamics of relativistic particles moving away. I don't remember if
talking about the prefactor KT.
Oh, I see this vorticity
KT prefactor, Boltzmann constant.
here.
Well, as you noted, thermal equilibrium proceeds in two stages. You have kinetic quickly, and the chemical one is a bit later. The quantum, my real question is, what is your experimental, what variable are you sensitive to experimentally that would allow you to probe the magnetic field which you alluded to?
So it's the momentum distribution of the particles which will be sensitive to the last scattering.
Vivek, your question.
I have a question. Are there any other vector mesons that you have the possibility to look at? That's number one. Number two, does this extremely high pulse